Okay, so now we look at something. Before we were arguing that normal variables show up all over the place. Now we'll see an important example of where you don't have a normal variable. Okay. This is the log normal. So why would you need such a thing? Well, your standard normal, for example, it can take negative values. And it's equally likely to take a negative value as a positive value. But there are things where there are situations in which negative values of the random variable don't make any sense. Right? So for example, stock prices. Right? Stock price could be 0, but it could not be negative. Okay? Now, let's take a look at, previously we talked about the sums of independent, identically distributed random variables, right? And so if I had a bunch of random variables and I added them together, they were all the same, basically the same random variable in the Central Limit Theorem. Okay, under all those conditions, we expect the sum is normal. Okay, what about products? If I take the product of a whole bunch of random variables, which are in fact basically the same random variable, with the same with the same mu and the same sigma, what do they look like? Would they look? Would that look normal? Oh, okay. Well, all right. So let's see. Supposing that I've got a product of random variables. They're x1, x2 up to xn. I won't specify what they are, but I'll say that they're basically the same. They're independent, identically distributed random variables. The same mu, the same sigma. And let's also impose the condition that the xi only take positive values. Because I want to take the logarithm of this product, and then I don't want to take logarithms of negative values. Okay? So I've got a product of these xi's, x1 through to xn, and these xi's are all taking positive values. Okay? What happens if I take the logarithm of this product? Now I've got log of x1 plus log of x2 up to plus log of xn, right? By the rules for logarithms, right? Logarithm of a times b is log a plus log b. Okay. Now, if x1 is a random variable, then log of x1 is a function of a random variable. It's a random variable. And if all of these xi are essentially the same random variable, then each of these log of xi's are essentially the same random variable. Whatever the PMF or the PDF is for log of xi, that's just being, okay? So I've got a sum of independent, identically distributed random variables. And if this sum has enough terms in it, how should it behave? It should behave like a normal distribution by the central limit theorem that we discussed the last time. Okay. So it's not that the product of independent, identically distributed random variables, which always take positive values. It's not that the product would be normal, but the logarithm of that product would behave like a normal random variable, according to the central limit theorem, provided that n is big enough. Okay. Okay, so that's what motivates this definition of the log normal random variable. If x is a random variable which takes positive values, and the random variable y equals log x, if that turns out to be, if this y, which is equal to logarithm of x, is normally distributed, then we say that x is a log normal random variable. Right? So there are some random variables which, if you take the logarithm, that results in a normal random variable. So we call such a random variable a log normal random variable. Okay. Okay, so how about this? Let's say y is normal. Then the exponential of y is a new random variable. Let's call that x. Now, if we take the logarithm of that x, we get y, and y is normally distributed. Right? So, random variables of the form x equals the exponential of y, where y is a normal random variable, these x's are log normal. Okay. Yeah.
When we say log, we're assuming log of t, right? But would the same be applicable to any other log?
Yeah. The various logarithm functions are all related to the natural logarithm through like a constant. So, yeah. Okay. Well, okay, let's look at its parameters. Okay, so, right, the logarithm, whenever I say log, it means natural logarithm, okay? All right, y, so let's go back here. Y is normal, so normal random variables have two parameters, right? Which we would say mu and sigma are the two parameters, or mu and sigma squared are the two parameters. If I say that y is normal, and I give you mu, and I give you sigma or sigma squared, then that gives you exactly what the PDF is, right? So if y has exactly two parameters, mu and sigma, and x, to make a log normal variable, I take the exponential of that y, then x also has two parameters, mu and sigma squared. But mu is not the expectation of x, and sigma squared is not the expectation variance of x. Mu and sigma squared are the expectation and the variance of y. Okay?
Act of log.
Yeah, y, which is equal to log x. Okay.
So they would also be variance and expectation of log.
Yeah, because log x is exactly y. Okay. Okay, so then how do we recover the standard normal from y? Well, the way we do it is standardizing any random variable to give you a new random variable which has mu equals 0, a new mu equals 0, and a new sigma equals 1. You subtract off mu and you divide by sigma. Right? So you get, if y is normal, and then you subtract off mu and you divide by its sigma, that gives you the standard normal. Okay? So if I want y in terms of the standard normal, then y is equal to sigma times the standard normal plus mu. Is that okay? Okay, so now if I exponentiate, right, the log normal random variable corresponding to this y is given by taking the exponential of y, right? So you take, that's the exponential, what was y? Y was mu z plus mu. So that's the exponential of mu plus sigma z. So every log normal random variable can be thought of as the exponential of some mu plus sigma z. So if you give me mu and sigma, that defines exactly what this log normal random variable is. Z is your standard normal. Yeah, so that this is taking values underneath the bell curve according to the PDF for the standard normal. Okay, all right, a bit of terminology. So in some applications, we call mu the drift, and sigma is called the volatility. Okay, so let's go back here. What happens if I make mu equal to 0 and sigma equal to 1? Then this x is the exponential of the standard normal. What happens if I make sigma equal to 0? Well, then x is just has the form e to the mu. X would become a constant. Okay? So you can, so we're going to relate this to stock prices in a bit. So mu is showing an exponential growth of the value of a stock, and sigma is the, so we call that the drift, and then sigma is a volatility around the stock price, right? So you have something which is deterministic, it's rising exponentially, but you've got some noise or volatility around that. And how big those variations are is controlled by that sigma. Okay, so once again, in some applications, like applications to assets which increase in value, mu is called the drift and sigma is called the volatility. Okay, so we know that the logarithm of x is a random variable with expectation mu and standard deviation sigma. We know what the PDF for the logarithm of x is, let's say. But what's the PDF for x itself? Right? PDF for x itself. I've already said that. Okay. So the PDF for x is 1 over sigma root 2 times x exponential minus logarithm of x minus mu squared over twice sigma squared. Once again, this sigma and this mu is coming from y. This is the standard deviation for y. This is the expectation for y. Okay? This isn't the standard deviation or the expectation for x. Okay? And we're dividing by x. Okay, so x has to be non-negative. And then if you try and put in any 0 or any negative value, this is equal to 0. Okay? All right.
Just more.
Okay, well, it's a bit of work to work this out, so I'm going to skip that. Okay. Okay. The CDF. Okay, what does CDF mean? It means the CDF evaluated at small x for x is the probability that the random variable takes a value less than or equal to x. That's given by integrating from minus infinity to x the PDF. Okay, so we have to integrate to get the CDF value at x for x positive. We have to integrate this from t goes from minus infinity to x, but from minus infinity to 0, the PDF is 0 anyways, so we only need to integrate from t equals 0 to t equals x. Okay. The expectation. This is going to be it's going to be non-trivial to try and do that. Well, we don't have to worry about it. Okay, so one reason that you don't really need to worry about that is that you can always relate your x to a normal random variable y, right, via the logarithm. So you can do a manipulation and then use your table or your software for the CDF of the standard normal, right?
The way we did it, like anytime we were making x, for example, a function of y function.
Yeah. Right. So if you wanted, okay, so here. The probability that x is less than or equal to x, okay, for x positive, that's also the probability that because logarithm has this behavior, right? It isn't oscillating going up and down. It's a one-to-one function. So I can just take the logarithm of both sides and nothing happens to this inequality, right? So that gives me that the logarithm of x is less than or equal to log of x, right? But what was logarithm of x? Logarithm of x was just y. Right? Oh, but now I can take y minus mu over sigma. And what's y minus mu over sigma? That's the standard normal. So let's just call it z is less than or equal to log of x minus mu over sigma. Oh, and this I can look in a table or online or something. Right? So yeah, I can use the Z table now. Okay. All right. Okay. So, in principle, this is what it is, but we're not going to. We don't really need to. Calculating values of this, these can be related to the values from a Z table. Okay. If we want the expectation, well, the expectation of x, you integrate x, well, let's say t times f sub x of t you evaluate from t equals minus infinity to infinity, but the PDF is 0 for non-negative values, so you integrate from 0 to infinity. And, okay, so you'd have to integrate. Have to integrate that.
Wouldn't that just be 1 over sigma root pi in the exponential of all of that divided by all of that? All of that's there.
See, you've got, in your exponential, you've got log of t squared, which makes it non-trivial to do this integration. Okay. Okay, so, but you can do a substitution. Yeah, you won't be able to do it directly. We try a substitution. Log of t, w equals log of t. And then you can get dw is equal to 1 over t dt, right? Okay. And then, oh, well, I'm not sure if that's making me any happier than I was previously, but this term in the exponential, I can manipulate that, and, well, okay. But then I go, oh, wait, I can manipulate it in such a way that I'm getting the PDF for the normal, right? And that should integrate to 1. All of this is the PDF for the normal, integrating from minus infinity to plus infinity. So that's going to give me this.
We don't have to worry about this derivation, right?
No. Okay. All right, so what do we get? We get the expectation of x. Okay, what was x? X was equal to, what was it? I'm sorry. Right. We had y equals log of x, right? And y was normal with some expectation and some standard deviation, right? Right? These are not the expectation and the standard deviation, right, of x, but of y. And what did we get? We get that mu sub x, or the expectation of x, is equal to e to the mu plus sigma squared over 2. Okay. Well, I always want to know at least the expectation and the variance. This variance is telling me how far values lie away from the expectation. Okay, well, if you do various manipulations and substitutions, you will get that this is your variance. Okay? And then the standard deviation would be the square root of that. Okay. All right. So how does it relate to anything useful? So this is one example. So we've got some asset at time equals 0, or let's say day 0. So we're going to look at what's happening every day. Let's say the closing price of some asset every day on the market. So S of 0 is the price of the security when we start tracking. S of 1 is after 1 day, S of 2 after 2 days, S of n after n days. So one of the models that's used is you look at how are successive, the ratio of successive days. So I look at S of n over S of n minus 1 to give me an idea of how the value of my asset is increasing or decreasing from day to day. Right? And I can call that X of n, for example.
Why would you not do this? Like S n minus S n minus 1 over S n minus 1?
How's that?
Why would you not take the difference as in?
Oh, yeah, you could take the difference, but usually we're looking at rates of return. We're saying, is this on average returning me 10% or something like that? So we're typically related to looking at fractions like this.
Here is X the normal number?
Yeah, X is going to be log normal. Right? Okay. So, okay. The real world is more complicated and simplified. In the simplest models for the stock market, this would be the case. Okay. So, if let's say we're looking at the price of some security, we would have to look at historical data to see. And we're saying we're going to model our X by historical data. So you do some parameter fitting. And you say, well, if I let mu equal this value, 0.000004, and I let sigma be 0.016, then that's a good fit to the data. And if you have, say, a software like R, for example, and you say, this is my model for the stock price, and it has these parameters mu and sigma, it will come back, and for something this simple at least, it will come back and give you an estimate of mu and sigma. Okay. So we're going to look at historical data to get this mu and sigma. We wouldn't be able to just have a theoretical reason for this mu and sigma. Yeah, this mu and sigma is are the expectation and the standard deviation for the logarithm of x. Yeah, exactly. Exactly. If we're supposing that x is log normal, right? Then these are the mu and the sigma, which relate x to a normal random variable y, and y would have this mu and this sigma. Right? Right? X has this expectation, and x has this, right? So we're giving you the mu and the sigma from which you could calculate the expected value and the variance for x. So this is a probability that x of n is bigger than 1. Okay? Right, so it's probability that the logarithm of x is greater than, take the logarithm on both sides. What's the probability that, since log is an increasing function, it respects the inequality sign. Right, so the logarithm of x is bigger than the logarithm of 1. That's the probability that the logarithm of x is greater than 0. Okay, but the logarithm of x is a normal random variable. So subtract off the mu and divide by the sigma of that normal random variable, and that will give you the standard normal. Do the same thing on the other side of the inequality. So that's the probability that z is bigger than this number, whatever that is. Okay, and then you read off of a z table. Okay, so since this is bigger than, you want 1 minus the probability that it's less than. Okay, you read that off of a z table, and you get this. Okay. Well, the probability will always be a positive number, right? Yeah.
Change which angle we're looking at it from. This can be assuming we're just above the
No, I think this is good. Yeah. Okay, so one example. If you look at actual stock market stock prices, there are criticisms about this model. It's not going to be exact, right? Okay. Product of independent, identically distributed log normal random variables. Okay. So, x and y are both log normal. They're both the same. They have the same parameter mu and the same parameter sigma squared. What can we say about their product? Okay. 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 If I take the logarithm of their product, what do I get? I got the log of x plus the log of y. Log of x is normal. X is log normal, so log of x is normal. Y is log normal, so log of x is, log of y is normal. What's the sum of two independent normal identical distributions? It's normal. So that means that, right? Remember, we've already had this discussion. If you sum two independent normals, what do you get? So that gives you a normal distribution with expectation 2 mu and variance 2 sigma squared. Right. So the log of the product is a normal random variable, which means that the product itself is log normal. Okay. The log of the product is normal, which means that the product itself is a log normal random variable. Okay. MGF, the moment generating function. So, as I said, the random variables that you most use, you'd want to have a table with their MGF, the first few moments, so on and so forth, right? Their PDF, PMN. Okay. Well, okay. The MGF doesn't exist. Okay, so this is our first example. The ones we were interested in, that we were using, the MGF existed, but this is an example of an important random variable for which the MGF doesn't exist. Okay. So if you want the moments, you have to do the hard work of some calculations. Okay. Let's say we have a log normal random variable. What about a scalar multiple of a log normal random variable? So x is log normal is 3 times x is a new random variable. Is 3 times x log normal? Well, okay. Well, if x is log normal, it's the exponential of a normal random variable. Or you can say that if I take the logarithm of x, I will get a normal random variable with some mu and sigma squared. Okay? Well, what if I have c times x? Well, logarithm of c times x is the logarithm of c plus the logarithm of x, and the logarithm of x is x is e to the y. And so if I take the logarithm, I get y. So the logarithm of c times x is a normal plus some constant. Okay. What if I have a normal random variable and I shift it by a constant? Well, you get a normal. The variance is the same, except you end up shifting its expectation. Okay, so if x is log normal, then c times x with c bigger than 0 is also log normal. And it has an expectation, the old expectation plus the logarithm of c, and the variance does not change. Okay. What do you think? Reciprocal of a log normal random variable. X is log normal. What about 1 over x? What do you think? So x is log normal. So if I take the logarithm of x, that gives me something which is normal with some mu and parameters mu and sigma squared. Okay. What if I take 1 over x? I get logarithm of, well, then I take the logarithm of that. So that's minus the logarithm of x. Now what? Right, so if this was y, then this is minus y. Y is normal. What about minus y? It's also normal, except the expectation is now you have minus the old expectation, and the variance doesn't change. Okay. Okay, so the sum of two log normals is not log normal. The product of two log normals is normal. And the reciprocal of a log normal is a new log normal. What about a power? Okay. So x is log normal. We have a new x to the a. A is not equal to 0. Okay? So x is equal to e to the y, with or y equals log of x, with y being normal, with some parameters mu and sigma squared. Then x to the a is equal to e to the a times y. Logarithm of x to the a is a times y. Well, y was normal. What's a times y? It's normal as well. With mu becomes a mu, and sigma squared becomes? Yeah, sigma squared becomes a squared. You're right. normal random variable is not even a good approximation. Okay? All right.